Welcome to the second week of advanced topics in plane geometry. Today we are going to introduce trilinear and bicentric coordinate systems. The topic today is a little bit difficult and maybe a little bit abstract and advanced to some of you. But this is a very useful tool so that if you know that, a lot of difficult geometry problems can be made easy. It is true that there's some learning curve towards these topics, but we are going to use the techniques in the future in the week 3 and later, and so you will have opportunity to be more to be familiar with it. Okay, so let's think about analytic geometry. So what is analytic geometry? So in analytic geometry, we set up a coordinate system. And using the coordinate system, we basically can convert a geometry problem into algebra, and we can solve the problem using algebra, and then we get the conclusion in geometry. So the idea is very good. The problem is that the coordinate system, called the Cartesian coordinate system, is a coordinate system that does not adaptive to a fixed triangle. So if it does not take into account of a fixed triangle, so that in a lot of cases, when you convert the geometry problem into algebra, it would be quite complicated, and sometimes it's too complicated to solve. The trilinear coordinate system is different. So trilinear coordinate system was first introduced by Proker in 1835. It is related, or it's adaptive to a fixed triangle. This is a kind of we call the homogeneous coordinate system. Homogeneous coordinate system, in the sense that we don't just use two real numbers, just like in the Cartesian, in the analytic geometry, we use a pair of real numbers to represent a point. In trilinear coordinate system, we use three numbers to represent a point. But these three numbers can be differed by an arbitrary, you can multiply the coordinate x, y, z by a non-zero number. Such a coordinate system is called a homogeneous system. So let me give you an example. So 1, 2, 3 in trilinear coordinate system is the same as 2, 4, 6. Okay, so in general, you can multiply 1, 2, 3 by any non-zero numbers to get the same point. Okay, so this kind of coordinate system is called a homogeneous coordinate system. Before we can introduce the trilinear coordinate system, we need the following new concept called the signed distance. We all know that in geometry, it is important to find out a point outside. If there's a point outside the line L, then you may sometimes want to compute the distance of the point to the line. So how to compute the distance? Well, starting from P, you need to draw a perpendicular line to L, and suppose the pedal point is H. So then PH, the length of PH is the distance, right? Okay, so we have a good formula in analytic geometry towards that. In geometry, in plane geometry, it is a little bit difficult to compute P of PH. But in analytic geometry, there's a good definition, there's a good formula to compute the distance. So let's say L, the equation for the L is written by Px plus Qy plus R equals 0. So that represents L in the Euclidean plane. Let P be x0, y0 be an arbitrary point. So this P could be outside the line or on the line, it doesn't matter. Okay, so there's a formula in geometry, in analytic geometry, that can be used to compute the distance. So the distance is given by this formula with the absolute value on Px0 plus Qy0 plus R. Okay, so what is the signed distance? The signed distance is just we drop off the absolute value. So in some sense, the signed distance is a much simpler object to study, except that the distance could be sometimes positive, sometimes negative. So let's take an example. So suppose this is L and the P is here. So assume that the distance of P to the L is positive on this side of the line. Then if I have another point Q on the other side of the line, then the distance, the signed distance is negative of the distance of Q to the line L. So why we have to introduce negative distance? Well, this is because if you look at this formula, you would see that this formula is much simpler than the corresponding formula using the absolute value. Just compare this formula to the formula px0 plus qy0 plus r absolute value over square root p squared plus q squared. Now, if we fix the line capital L, then both formulas are functions of x0 and y0. But this formula is much simpler because this is simply a linear function of x0 and y0. And this is much more complicated because you start with a linear function, you take absolute value. And when you take absolute value, a function is a composition of a function with the absolute value. So it does not have as many applications of the signed distance. Okay, so I already write this here, and so when the distance, signed distance becomes positive, when the signed distance becomes negative, well, it does not just depends on the line, but also depends on the so-called orientation of the line. So it's more or less arbitrary. You can define, okay, so this line L, above L, any points the distance is positive, and the other side below L, the distance is negative, or vice versa. So it depends on the line and the one orientation, which you can designate one area to be positive, the other area would be negative. Okay, so this is the signed distance. In analytic geometry, we can use signed distance, sometimes we can even use signed area, in the sense that, well, if you have a triangle and the height can be made sometimes positive, sometimes negative if you use the signed distance, and then you would get signed area. But we probably don't need this today. Okay, so now let me introduce the trilinear coordinate system. So the trilinear coordinate system is adaptive to a fixed triangle. So in the Euclidean plane, let me fix a triangle ABC. And then we choose the orientation of lines BC, CA, and AB. Obviously, BC, CA, and AB defines three lines. And so we will assume, so this is forcefully, we will assume that any point inside the triangle and their signed distance to the three sides are all positive. So this is a reasonable assumption. So that if P is somewhere here, below BC, then its distance to BC is negative, but its distance to both AB and AC would still be positive because C has positive distance to AB by our orientation, by our assumption, and then this is on the same side of AB, same side of the plane of AB. So a point here has negative distance to BC and two positive distances to AC. Okay, so let x, y, z be the signed distance of x to the three sides of the triangle. Here, our convention is always like that. So if we have a triangle ABC, then the distance to BC would be assigned x. The distance to CA is the second distance, and the distance to AB is the third distance. So this is because the corresponding BC is corresponding to angle A, CA is corresponding to angle B, and the Z is corresponding to angle C. So we just write the coordinates in that order. And the trilinear coordinates of P are the ratios of its signed distance. We don't need to know exactly what the distance is. We just need to know their ratio. And the ratio would give us a trilinear system of the point P. So there's a unique way, if you can use x, y, z, there's a unique way to determine P. In fact, there's a transformation from trilinear coordinates to Cartesian coordinates. Okay, so before we discuss those theoretical questions, whether or not any point would have unique trilinear coordinates or not. So we will skip those theoretical questions and go direct to the applications. And in fact, we can compute some of the trilinear coordinates of some of the special points of a triangle. Okay, so that means basically we will skip the second section called the basic properties of trilinear coordinate system. So basically I will skip that, but in theorem 1 we basically proved that this trilinear coordinate system is indeed a coordinate system. What do I mean? So just think about the Cartesian coordinate systems. We know that a pair of real numbers represent a point on the plane. Okay, so this correspondence is unique. Any point has the unique coordinates, and any coordinates represent a unique point. You won't have have the situation that one point on the Euclidean plane can be represented by two pairs of real numbers. That's simply not true. For the trilinear coordinate system, we want to prove the same result. Any point can be represented by a unique trilinear coordinate system. So that means if x, y, z is proportional to x1, y1, z1, they basically represent the same point. So that needs a proof. We will skip this theoretical question, but I want you to pay attention to this formula. So this gives us the invariance or the relationship of the coordinate system with the triangle area. And there's a homework problem that I will post to use this formula to prove the Viviani theorem. You will see that in the homework. Okay, so first question. So once you have triangle ABC, so what is the trilinear coordinate system coordinates? What are the trilinear coordinates for the point A, B, and C? Okay, so for example, what is the trilinear coordinates of A? So just think about this. Think about the distance of A to BC to CA to AB. Okay, so first A to BC is a positive number, which is the height. Okay, so this distance x is equal to h. And the y and the z are simple because A is on the lines AC and AB, so the distance to these two are zeros. So the trilinear coordinates of A is actually h0, 0. Or I prefer to write it as h0, 0. However, this is a homogeneous coordinate. So that means if I multiple a real non-zero real number to the whole coordinate system, I don't change it. So if I multiple the reciprocal of h to this, so we would get 1, 0, 0 because I multiple 1 over h to all of 3, I get 1, 0, 0. And so this would be the trilinear coordinates of the point A. So by the same reason, B has the trilinear coordinate 0, 1, 0. C has 0, 0, 1. That's pretty simple. Okay, so how about, let's say I have a midpoint D of BC. What is its trilinear coordinate system? Well, just think about this. The distance of D to BC is equal to 0. So x is equal to 0. And the distance of D to AC and AB. Okay, so these two distances, and what are they? Well, you will see that it depends on the angle. So this angle, let's say, is gamma, this angle is beta, this angle is alpha. So this is DE, DF. So Y is equal to DE, that's equal to DC times sine gamma. And Z is equal to DF is equal to BD times sine beta. Okay, so the trilinear coordinates of D would be 0, DC sine gamma, BD sine beta. But our assumption is that D is the midpoint. So that means DC is equal to BD. So actually I can cancel them. I can multiple the reciprocal of DC and the BD. I can basically cancel them. So the trilinear coordinates of D would be 0, sine gamma, sine beta. And you know that since the triangle ABC is fixed, so sine gamma and the sine beta are fixed number. So you can compute them. Okay. All right, so let me skip section 2. And so let's go to the most interesting part and the most powerful tool for the so-called 5 triangle centers. So in triangle, there are 5 important centers. Actually, there are more than 14,000 triangle centers listed, people now discovered. But the top 5 are the most important. And they play one of the central roles in triangular geometry. And so today, let's very quickly go over these 5 triangle centers. And the point I want to make is that we can easily compute the trilinear coordinates of those triangle centers, and we can make use of them later. All right. So the number 1 center for a triangle is called the incenter. Okay. Did I have? Okay, I don't have a picture for that. Do I? So this is the centroid, so I will draw one. So if we have a triangle, and what is the incenter? Incenter is the center of the inscribed circle. Let's see if I can adjust that to make it tangent. Okay, it's a little bit hard. Anyway, so suppose this circle is tangent to all 3 sides of the triangle. Then the center we called I. So I is called incenter. Okay, and the reason that it is called the incenter is because this is the center of the inscribed circle. Okay, this is the incenter. So what is the trilinear coordinates for the incenter? Well, this is the point such that to all the 3 sides, the distance would be equal to the radius of the inscribed circle. So the trilinear coordinates would be, suppose the radius is r, so r to r to r, that's equal to 1 to 1 to 1. So the trilinear coordinates for the incenter is 1 to 1 to 1. And from this, you will see the power of trilinear coordinate system. So if you just insist to find the distance, then you need to find the radius of inscribed circle. And that's a complicated, there's a complicated formula to that. But actually, r to r to r can be cancelled because we only care about the ratio. The ratio is 1 to 1 to 1. And that is the coordinates, trilinear coordinates for the incenter. And you probably have known that there are 3 x-scribed circles. I don't know how to draw them, but it's tangent to one side and the other extended side of triangle. There are altogether, there are 3 we call the x-scribed, how to spell, ascribed circles. And so what would be the trilinear coordinate for those x-centers, meaning the center of the ascribed circles? So let's take this for example. The distance to all 3 sides are again the same. But if you count the signed distance, well, as we mentioned before, the distance here should be negative and the other 2 would be positive. So the x-center corresponding to the angle A, it would be equal to, well, -1 to +1 to +1. And the other 2 would be 1 -1 1 or 1 1 -1. So basically we solved, we find our first non-trivial trilinear coordinates for a special point of the triangle. Okay, so the trilinear coordinates for the incenter is 1 1 1, and the x-centers will be 1 -1, the other 2 would be +1. Okay, for the other centers, the computation is not that easy. So the next one I'm going to I'm going to compute is the trilinear coordinates for the so-called centroid. So what is the centroid? Okay, so the centroid is the point that, well, it is the intersection of the three medians of a triangle. Okay, so three medians. So if we have a triangle ABC, and if D is the midpoint, so AD is called the median. Is called the median. And so by Siva theorem, we learned last week, we know that the three medians has to be concurrent. So they meet at one point. Okay, so that one point is called the centroid, G. And so the question is, what is the trilinear coordinates of G? Well, the computation could be tricky. There are two ways to do that. You can either use the area method or use what? Using similar triangles. Okay, so here we use the area method. So by the property of the centroid, we know that the area of the triangle GBC and the GCA and the GAB are all the same. So these are all the same. Okay, and so therefore we know that if you set up XYZ to be the distance to the three sides, then we would have AX, half of AX equals half of BY is equal to half of CZ. And therefore XYZ is basically equal to the reciprocal A minus 1, B minus 1, C minus 1. Okay? So because AX equals BY equals CZ, let's say equals K, so X is K times the reciprocal of A, K times the reciprocal of B, K times the reciprocal of C. So their ratio is A minus 1, B minus 1, C minus 1. So if we use the law of sines, we know that A is equal to 2R, where R is the radius of circumcircle, sine A, B is 2R sine B, C is 2R sine C. If you do that, then, and if you take the reciprocal of ABC, then the trilinear coordinates would be cosecant A, cosecant B, and cosecant C. So this gives us the trilinear coordinates for the centroid. Okay, so we have introduced the in-center, the x-center, the centroid is the third one, and we have two more. Okay, so the next picture is the center of circumscribed circle. Okay, so for any triangle, there's a unique circle that passing through all the vertices A, B, and C. And the center is called, of such a circle is called the circumcenter. So here's the question. What is the trilinear coordinates for the circumcenter, which I call O? So in the following picture, you would see that you need to find the distances from O to BC to CA and to AB. And so how to compute X, Y, and Z? And here we have to use a little bit Euclidean geometry to find out the angle here. So what is the angle here? Okay, so this angle is actually half of the angle. So angle BOD is half of the angle BOC. Why? Well, because OB is equal to OC, because both of them are equal to the radius of the circumscribed circle. And so triangle OBC excuse me, is a isosceles triangle. And for isosceles triangle, if OD is perpendicular to BC, so then OD is an angle bisector of the angle OBC. So therefore, half of the angle OBC is equal to angle BOD. However, angle OBC is called the central angle, which is twice to the inscribed angle A. So this is actually equal to A, right? So the angle is the inscribed angle, and this is the central angle. The inscribed angle is half of the central angle. So the conclusion is that angle BOD is actually equal to angle A. And by trigonometry, we know that x is OB times sine of angle BOD, which is sine A. But OB is R sine A. Okay, very good. So, sorry, here is cosine. This is line, this is adjacent leg. So this is cosine A, cosine A. Okay, by the same reason, you would find that y is r cosine b and z is equal to cosine c. And so therefore, the trilinear coordinates would be their ratios. So you can cancel capital R, and you can tell that the trilinear coordinates is cosine A by cosine B by cosine C. Well, this is just one of the representations of the triangle system of the circumcenter. If you want, you can put two, but you may want to cancel them. By the same reason, you don't want to keep R, because the computation of R is complicated, so you don't want to do that. So this probably is the simplest form of the trilinear coordinates of the circumcenter. Oh. Okay. So the last one, probably is the most difficult one, is called the orthocenter. So from the last week, we know that the three heights or the three attitudes of a triangle must be concurrent. Okay, and that will be concurrent at the point H, which we call the orthocenters. Orthogonal is equivalent to perpendicular. Okay, so therefore, the orthogonal center, the perpendicular center, is basically called the orthocenter. Okay, so there are some trigonometry we have to use in order to find the coordinates, the trilinear coordinates of H. Okay, from this picture, we know that we just need to compute HD, HE, and the HF. And since the triangle is symmetric, I just need to compute one, and the other two can be found in the similar way, can be using the same way. Okay, so let's work on this picture. So assume that EBC is equal to alpha and the CAD is equal to beta. And we will see that this HD would be BD times tangent alpha from the picture. Okay, tangent alpha is BD over HD. Tangent alpha is HD over BD, multiplied by BD, you get HD. Okay, so but this alpha is supplement to here. They add together to be equal to 90 degrees. So tangent A would be equal to cotangent C. Nice. And what is BD? For BD, I would use this. Okay, use this right triangle. Let me erase that. So how to compute the BD? Well, BD is equal to AB cosine B. Okay, so this will be equal to AB cosine B. But this is still not symmetric enough. So let's use the law of sines to represent AB as 2R cosine C. Okay. Okay, there's a typo here. Okay, I made right things wrong. AB is tangent beta is BD cotangent C, which is fine. But BD is cosine B cotangent C. And okay, so good. I'm fine. Cosine B cosine cotangent C. Let's see. Okay, maybe there's a typo. Cotangent C, but AB is okay. AB is 2R sine C. That's 2R here. But cotangent C is cotangent sine C. This is cosine C. So anyway, so in the end, we would get 2R cosine B cosine C. So similarly, we would have HE to be 2R cosine A cosine C and FH to be the other way around. So one way to write the trilinear coordinate system of H would be like this. And you can cancel R as usual. But this is still not in its simplest form. So how to further simplify this expression? I can divide this coordinate by cosine A, cosine B, cosine C. So like the first term divided by cosine A, cosine B, cosine C, you would have 1 over cosine A, which is secant A, and then secant B, and then secant C. So that would be the trilinear coordinate for H, for the orthocenter. So these are the basic computations related to trilinear coordinate system, as well as a little bit of trigonometry. Okay, so these results are important, and I hope you can go over with that after the class. And in the homework problem, you will have an opportunity to use these coordinates to prove some interesting results. Okay, so 5 centers, let's go over. In center, number 1, number 2, X centers, centroid, circumcenter, and the orthocenter. These are the top 5 centers. These are the most important triangle centers. And if you look up in Google, you would find there's a web page that contains 14,000 triangle centers, but most of them are useless. Okay, so bicentric coordinate system, it's somehow very closely related to trilinear coordinate system. So in most cases, you just need to know one, and you can easily transform back and forth to the other coordinate system. So bicentric coordinate system is important not only in Euclidean geometry, but also in applied math. So if you go to college, you probably will see bicentric coordinate system for one more time if you study computer science or numerical analysis. Okay, so again, let's fix the triangle ABC. And this time, let's assume that the 3 sides of the triangle BC is equal to A, CA, the length, is equal to B, and AB is equal to C. So let P be any point in the plane, let XYZ be the trilinear coordinate system. So then AX, BY, CZ is called bicentric coordinates of P. So basically, it's just differed by XYZ becomes AX, BY, and the CZ. So if you know 3 sides, which of course you know the 3 sides, the length of 3 sides of a triangle, because triangle ABC is always fixed. And then you can convert the trilinear coordinate system to bicentric coordinate system, and you can transform back. Okay, you will have one problem that you need to do for bicentric coordinate system. So just remember, for the trilinear coordinate system, the in-center has coordinate 1, 1, 1. Under the bicentric coordinate system, the centroid has the coordinates 1, 1, 1. Because why? Because AX is twice of the area PBC, and the PCA and the PAB, they are all the same. So you have 1, 2, 1, 2, 1. Okay, I will also skip this converting problem, converting between Cartesian and the trilinear coordinates. So there are a few computations which are useful, but I don't have time, so I will skip that. So this would be a interesting reading using a little bit algebra. Okay, this will help you to understand the algebra a little bit better. Okay, but let me skip that. Okay, so this is a more or less advanced topic called the determinant. So you will see determinant in college algebra, but it's for 3 by 3 matrix. Its determinant, probably you have already heard of that if you prepare for AMI. Okay, so here we listed a formula for the determinant of a 3 by 3 matrix. But for 2 by 2 matrix, the determinant is easier. So the determinant is equal to AD minus BC. Okay, so this is the determinant for a 2 by 2 matrix. For 3, but in our trilinear coordinate system, in the problem related to trilinear coordinate system, we sometimes need to compute the determinant of a 3 by 3 matrix. And this formula looks quite complicated. The way I can memorize it is as the following. So we have this table of 3 by 3 matrix. I will start with AEI. So totally there will be 6 terms. But I will start with this AEI, and then BFG, and then DHC. So each time you pick up one number, and so then you pick up the second entry. Sorry, not one entry, and the second entry which does not have the same rows or columns with the first one, and then you pick up the third. So then you using this, you are able to find the first 3 positive term. And for the negative term, you go to the other way around. So this is the second diagonal for the matrix. Okay, so maybe I can erase it because it's not easy to read. So this is the other diagonal. Okay, CEG, but then this one would be negative. And there are other 2 negative terms coming from the same way, but the different orientation, okay? So the red one is from top left to bottom right, and the blue one is the other way around. Anyway, so CGE, and the AFH, and the last one would be BDI. Okay, so altogether there are 6 terms. So you probably needed to do a few examples by yourself, compute a few examples by yourself, and to be familiar with this formula. So the concept of determinant is important, and you probably need to do some computation someday. Okay, but this theorem is important. Okay, so suppose ABC be 3 points. I'm not saying ABC forms a triangle. Let's say let's give ABC. Let's assume ABC be 3 points on the Euclidean plane, and suppose that they have trilinear coordinates A1, B1, C1, A2, B2, C2, and A3, B3. Why I write C3? Okay, sorry, there's a typo. A3, B3, C3, respectively. Then there's a nice criterion for ABC to be collinear. So they are collinear if and only if you just need to compute the determinant. And if determinant is equal to 0, so that means capital A, capital B, and capital C are collinear. And if they do collinear, then the determinant is equal to 0. So that's what I mean if and only if. So either way is correct. Okay, so while this determinant probably you're still not familiar with it, this gives you a very easy, very nice criterion to determine whether 3 points are collinear or not. Just think about this. We have very few geometric tools to prove that the 3 points are collinear, right? And so this algebraic criteria will be the definite way to determine whether 3 points would be collinear or not. So this is a nice criterion. And for the rest of the talk, I will lead you to show you to do some work and using this criterion. Actually, I will give you 3 examples. Okay, and so the first example is, well, we know that by Siva theorem, we know how to compute. We know how to prove that the 3 medians are concurrent. Can we use the concept of trilinear coordinates to do the same thing? Well, of course, yes. And so let's do it. So this is A, B, and C. So how to prove that the 3 medians are just that they are concurrent, they intersect at one point? Well, by what we have learned, we just need to prove that any median, say AD, would pass the centroid. And the centroid has already, we already know its trilinear coordinates would be A minus 1, B minus 1, C minus 1. We just compute it. Okay, we know its coordinates. And we know that A has the coordinate, so this is G. Okay, let me write it here. So G has coordinate A minus 1, B minus 1, C minus 1. How about A? A is 1, 0, 0. We just computed. How about D? We computed D also, and basically D would be equal to 0. I said sine gamma, sine C, and the sine B. Okay, am I right? So let's say this. Okay, but you can rewrite this in terms of ABC, because by the law of sines, we know that sine A, sine B, sine C are proportional to ABC. So since we don't care about an arbitrary constant, so I can write this as CB. Okay, so now we are ready to determine whether A, G, and D are collinear. If we can prove A, G, D 3 points are collinear, by the same argument, we can prove that the B, G, E and the C, G, F are all collinear. And so that's another way to say that the 3 medians are concurrent at the point G. Okay, so how to determine that? Well, we will compute the determinant of A minus 1, B minus 1, C minus 1, 1, 0, 0, 0, CB. Okay, so we are going to determine whether this determinant is equal to 0 or not. So you may say, why you write G as the first row, the coordinates for G as first row, A as second, and the D as the third? Well, my answer is it doesn't matter. Okay, so in linear algebra, we will know that if you use different ways you rearrange the rows of a matrix, then the determinant can at most differ by a negative constant, negative 1. And since we are going to prove that this determinant is equal to 0, so even negative 1, negative sign doesn't play a role here. Okay, so how to compute? So let's compute the determinant of this matrix. So using our rule, there are easy ways, but using our rule, this one would have 3 positive terms. This would be the first positive term, A minus 1 times 0 times B. The good news is that this first term is 0. So in mathematics, something is equal to 0 is always perfect. Okay, it is the problem is sometimes it's non-zero, then you have to do some research. If it's 0, that's perfect. Well, the first term would be 0. The second term is again 0 because you have 1, 0. The third term is not 0. B minus 1 times B, that's equal to 1. Okay, so next, let me use a different color to figure out the negative terms. So this would be the first negative term, but that's 0. And you would have, okay, I'm sorry, I made a mistake, I guess. Let me go back to here. First red term is 0, second red term is 0, the third red term is 1. So this is the third red term. It's C plus multiple C minus 1, and okay. And so now let's go back to the other side, the negative terms. The first negative term is 0. The second negative term, because there's a 0 here, it's 0. But the third negative term, which, okay, it's messy, would be 1. So you will see the final answer would be 1 minus 1. That is going to be equal to 0. So that means A, G, and D are collinear. And you proved that 3 medians are what? They are concurrent. You can, in fact, to use this idea to prove other things, like the 3 heights, why 3 heights are collinear, are concurrent. Well, you can do the same thing. And why 3 angle bisectors of a triangle must be concurrent. So you can use this to prove a lot of things. Okay, in fact, you can use this to prove that all these 5 centers exist. Existence means, well, even for circumscribed center, it is the intersection of the three perpendicular bisector lines. Okay, and you can use trilinear coordinates to prove them all. Okay, so this is our first example. The second example is, surprisingly, when I prepared this class, I just found out that I can use trilinear coordinate system to easily give another proof of Menelaus theorem. Okay, so what is the Menelaus theorem? Well, suppose ABC is a fixed triangle and the DEF be 3 points on the line BC, CA, and AB respectively. So part of the Menelaus theorem states that if this guy is true, then DEF must be collinear. So how to prove it? So last time we used similar triangle and area methods to prove it. And today I'm going to use trilinear coordinate system to prove that DEF are collinear. Okay, so how to do that? Well, the key would be how to compute the trilinear coordinates for DE and F. And once you computed it, you are done. Okay, excuse me. Let me start with finding the coordinates of E, okay, instead of D, because D is a little bit complicated because D is not on BC, but on the extended line of BC. But it's the same, but you would have negative sign. So let's first compute E. So E is a point on the line AC. And the related ratio would be CE by EA. So for the sake of simplicity, let me do the following. Okay, let me do the following. I will say this angle is equal to alpha, beta, gamma. So these are the fixed angles. And the number two is that I want to assume that this guy is equal to lambda, this guy is equal to mu, and this guy is equal to nu. Okay, so what we want to prove is lambda mu nu. So we want to prove is that the lambda mu nu is equal to 1 or maybe equal to negative 1. Well, equal to 1. Okay, so now let's say how to compute the coordinates of E. So the trilinear coordinates. So the coordinates E. So let's compute the distance of E to BC and the E to AB. Okay, so this is X. So let's say this is Z. Okay, the distance of E to AC is obviously equal to 0. So we already have the experience when E became the midpoint of AC. So we are able to do that. But now let's say in general we can do this as well. So the point is that suppose this is X, this is Z. So X would be equal to EC sine gamma, and the Z would be equal to EA sine alpha. Okay, so Y is equal to 0. So for E, the trilinear coordinate would be EC sine gamma, EA sine alpha. Sorry, in the middle should be equal to 0. And so then EA sine alpha. Okay, so how to simplify this expression? Well, we realize that CE over EA, CE is EC, that's equal to mu. So if I divided all three components by EA, so I would get mu sine gamma, 0, and sine alpha. So that would be the coordinates for E. Okay, so let's compute the coordinate for F. And you can imagine this would be for F, the distance to AB is equal to 0. So the last term has to be equal to 0. And what in the middle you have similar pattern to BC would be, okay, so let me use different color. Should I erase that? Otherwise it's too complicated. So let's erase that. And let's compute the distance F to AB and F to AC. Again, the distance to BC, the distance to BC is marked as X, and so this is X, this is Y, and this make this to be Y. So the question is, what is X by Y? So yeah, so let me write down the final answer directly. Okay, maybe I can't. Let me do the computation. Let me erase this first. Maybe I can write here. So X is equal to FB sine beta, and the Y is equal to FA sine alpha. So their ratio, F, would look like FB sine beta, FA sine alpha, and 0. So again, AF, FA divided FB is equal to nu. So this, if I divide it by FB to the 3 components, I would get sine beta nu sine, okay, this nu is too similar to gamma, but they are different Greek letters. Okay, so this is F. Okay, so now let's compute the coordinates for D. So the method for computing D is the same. The only problem is D on the outside is a point that outside the triangle. And when this is outside triangle, you have to determine the negative sign, because we are talking about the distance is not the true distance, but sine the distance. So let me erase this again. And since D is on BC, so its distance to BC is equal to 0. So we need to talk about its distance to AB and its distance to AC. Okay, so that's the distance. And so again, let me make this to be Y, and this to the distance of D to AB to be Z. AB is always the last one. This is to be Y, and this is little z, this is little y. Okay, so let's say Y would be dc times sine gamma, right? Sine gamma here. And z would be equal to, well, this is angle beta, dB sine beta. However, we will see that y is d is outside the triangle, so its distance to AB, which is z, should be negative, because this is on the AB, the other side of AB, other than the point C. However, its distance to AC is considered positive because it is on the same part, same sides as B. B to AC is supposed to have positive distance. Anyway, so one of them is negative, one of them is positive. So let me write out D, which is 0 dc sine gamma negative dB sine beta. And we know that BD over DC is equal to lambda. So I divided by BC, DC on both sides, I will get sine gamma negative lambda sine beta. Okay, very good. Now let's compute the determinant of this, the matrix obtained by these 3 points. So determinant of, the order doesn't matter, mu sine gamma 0 sine alpha sine beta nu sine alpha 0 0 sine gamma negative lambda sine beta. So let's see. So this would be, the positive sign would be negative lambda mu nu sine alpha sine beta sine gamma. So that's the first term, positive term. The other one would be this one, 0 0 0 is 0, but the other way around will be plus sine alpha sine beta sine gamma. And so the nice part of the other 3 negative terms, they are all 0, because no matter what you do, you will encounter a 0. So you basically get this to be 0, because we by our assumption, lambda mu gamma is equal to 1. And when lambda mu gamma is equal to 1, so these 2 terms are cancelled, you will get a 0. So that confirms that the Menelaus theorem using the trilinear coordinate system. Okay, so in most cases, well, I shouldn't say most cases, in a lot of cases, when you are if you want to prove that the 3 points are collinear, then finding their trilinear coordinates, that will be good. That will be easy to solve the problem. Okay. All right. So that's the reproof of the Menelaus theorem. You can reprove the Siva theorem as well. The last one, the last example, is actually a famous example. So this we mentioned the 5 points, and in fact, it was Euler who was the first one to notice that 3 of these 5 points are actually collinear. What are these 3 points? The orthocenter, the centroid, and the circumcenter. They are collinear. And you can Google, so this Euler line is a very famous line. You can Google and find that the purely geometric proof of this fact is not easy. Okay, and now let's use trilinear coordinate system to prove that these 3 points are collinear. And since we already computed since we have already computed, so this probably is redundant. I don't need this anymore. We computed the trilinear coordinates for all these 3 points. So that means we just need to verify this identity. Okay, so the first row is the orthocenter, the trilinear coordinate for the orthocenter, secant A, secant B, secant C. The second one, cosecant A, cosecant B, cosecant C, would be equal to the centroid coordinates, and the circumcenter would be the last one. So how to prove that this determinant is equal to 0? We have to use a little bit trigonometry and a little bit, well, let's see how we can do that. So secant and the cosecant are the trigonometric formulas that is 1 over sine or 1 over cosine. When you have something in the determinant, so then you multiply them by the common determinant. So this is what I will do. Okay, so for a determinant, whether or not a determinant is not 0, it doesn't matter if you multiply a non-zero number to each row or each column. So here, what I want to do is in the first row, I multiply by cosine A, cosine B, cosine C, and I multiply to each entry of them, which I will get, well, the first term will be sine B, sine C, because okay, I maybe switch back. Okay, I should switch that. So multiple this will be, you will get cosine B, cosine C, and so cosine C, cosine A, cosine L, cosine B. Multiple this guy by sine A, sine B, sine C, you would get that. Okay, so now how to prove that the determinant of this matrix is equal to 0? It looks like we make things even more complicated. Well, don't worry. There's a constraint of the 3 angles. In a triangle, we know A plus B plus C is equal to 180 degrees. So therefore, we know that this cosine A is actually equal to negative cosine B plus C. Okay, it's equal to negative cosine 180 minus A, which is equal to BC. But then cosine B cosine C is negative cosine B cosine C plus or minus plus sine A of sine B by the addition formula. And you basically see that the last row, can be written as, so if you subtract these 2, basically negative, subtract it, you get that row. And so therefore, using linear algebra, which I didn't mention, but if you 2 rows adding or subtracting, and you can get the third row, that means the determinant is equal to 0. So that's what we have done. Okay, so this proved that these 3 of the 5 centers are actually collinear. So this line is called the Euler line, and this is a very interesting line in geometry, and we will see more interesting you will see more interesting lines in the homework and the materials we are going to talk about next week. Okay, I will stop here today, and please do the homework, and please, if you have any questions, you can go to the office hours. This week, the office hour will be Wednesday, July 29th from 4 to 5 p.m. Okay, so talk to you later.